Good morning, children. Now today we'll talk about potential. The two phenomena which are associated with the static point charge. One was electrostatic force, for which we got the formula as, according to Coulomb's law, 1 by 4 pi epsilon naught Q1 Q2 upon R square. Then we found out electric field due to a static charge, which was equal to F upon Q naught tending to 0, and the formula was 1 upon 4 pi epsilon naught Q upon R square. And the direction of electric field was the direction in which the test charge will move if it is kept in that electric field at that point. See, this is an expression for finding out intensity of electric field or strength of electric field at a point. Now the third topic or the phenomena which we are going to talk about is potential, which we denote by V, and the formula which we will get is 1 by 4 pi epsilon naught Q upon R. And now you can remember these formula in continuation. See, here there are two Q. So one of the Q vanishes when we come to electric field, and one of the R vanishes from here when we come to potential. So in this way you can remember the formulas. Now potential here is defined either at a point or we define potential difference. In general, we will not define potential. Potential will always be defined at a point, certainly in the electric field, or we will define potential difference. To find out a mathematical expression for potential at a point and potential difference, first we find out an expression for potential difference, and then that expression can be limited for finding out at a point. Now what actually is the concept of potential difference? See, potential difference we have done in class 10th also, and it is the work done in moving a unit charge from one point to another in the electric field. So we'll try to find out an expression for potential difference. Let us consider a charge Q whose electric field is, say, this board, and I want to take a charge, say Q naught, we'll take the test charge Q naught, from a point, say A to say point B. Work done in moving a charge from A to B we are going to calculate. Now this will be defined mathematically as potential difference. What I am going to find out? Potential difference between points A and B. So this will be equal to the work done in moving the charge from A to B in the field divided by the test charge which is being moved. The distance of the point, say B from Q is RB. Distance is increasing in this manner. Distance of point A is increasing this way. So the distance is, say, RA. Let us start moving the charge Q naught from A to B. Let us consider that we have reached at a point P at a distance, say R, from the charge Q. I'll again repeat. In the electric field of charge Q, I am going to move a test charge Q naught from point A to point B. And certainly, as you know, as you will keep on bringing the charge from A to B, work has to be done. The reason being, see, this point A is in the electric field. I'll put a test charge. This is already a charge over here. This is going to exert a force on Q naught in this direction. So to bring it back towards the charge, I'll have to do some work. And that work or that force which will apply to bring nearer will keep on changing. Because displacement or the distance from charge Q is different. Work is force into displacement. So it will keep on changing. So this is a case of variable work done. And whenever we talk about a variable quantity in continuation, we'll have to go in for integration, taking the limits. So I'll take any point P, say at a distance R. Now how much will be the force experienced by the charge Q naught at point P? Suppose the electric field produced due to the charge Q is E. So a force will be experienced by the test charge Q at point P, which will be equal to F is equals to Q naught E. In which direction? In this direction. We have already said that E is equals to F upon Q naught. Now to make this charge move in this direction without any acceleration, we are not going to increase the speed, but we have to take it towards left hand side. The force required will be minus Q naught E, which will have this direction. So to move towards this direction, from P, as soon as this charge Q naught starts, is being forced to move towards Q, a force this much will be required to move it towards this side without any acceleration. Now we have to take a very small displacement, assuming that force remains same. पॉइंट P पर कितना फोर्स लग रहा है? F is equals to Q naught E. इसे P से इधर ले जाने के लिए हमें कितना फोर्स लगाना पड़ रहा है? F is equals to minus Q naught E. Let us consider a very small displacement dl towards A to B, or from point P towards the charge Q. Assuming that force remains same, so the small work done, every time I am not going to write down AB, but it is the work done in moving from A to B, and this is the small work done, so we are not writing A and B again. So the small work done will be equal to force into multiplied by displacement. See, work is a scalar quantity. force into displacement. So what is force? Minus Q naught E into dl. This is the force being applied to the charge Q naught at point P to move towards B. But I want to find out force from A to B. In the next step, what we are going to do is, what is the angle between E and dl? E is directed towards this side, away from the positive charge, and dl towards positive charge. So the angle will be 180 degree. So it will be cos 180 degree. This is going to give me plus Q naught E dl. Now electric field at point R is 1 by 4 pi epsilon naught Q upon R square. Now this Q naught into dl. That means for finding out work done, I'll have to integrate in terms of dl. See, we do not have any term of dl in this expression. But we know that dl is connected to r. So dl either has to be written in terms of r or r has to be written in terms of dl. So how will we write? dw is equals to 1 upon 4 pi epsilon naught Q upon R square Q naught. And now see, dl is having direction against R. R is increasing in this manner. dl is increasing in this manner. So since they are vector quantities, so one is negative of the other. So dl is minus dr. And now we can integrate. See, minus, this is constant. Q naught is also constant. Integration dr. And we are moving from RA so now integrating, how will you do it? Now this is not a constant, now this is variable with R. So this will come here. So how will you integrate? Minus 1 by 4 pi epsilon naught Q naught. Integration of this is going to give me minus 1 upon R. RA to RB. Why minus? If you remember the formula is x to the power n dx is equal to x to the power n plus 1 upon n plus 1. So here what we are going to get? R to the power minus 2. And r to the power minus 2 will give me integration r to the power minus 1 2 plus 1 minus 2 plus 1. That will give me r to the power minus 1 upon minus 1. So minus 1 upon r. This will be the integration. We will substitute the limits. So what I am going to get? W is equals to minus 1 by 4 pi epsilon naught Q naught minus 1 upon, you can take this negative sign inside. So I will obtain what? Keep it here only. First we will substitute the values. 1 minus 1 upon RB and minus 1 upon RA. So plus 1 upon R. Now I'll change with this negative sign. I'll take it inside. So what I'll get? 1 upon 4 pi epsilon naught Q naught 1 upon RA minus RB minus 1 upon RA. This is, see, minus 1 upon 4 pi epsilon naught. This minus I have taken outside. Q naught dr upon R square. So the integration will be minus 1 upon R minus 1 upon RB minus 1 upon RA. So this is my expression. This is for expression WA upon WAB. Now VB minus VA, already what we have written, work done upon Q naught. So my answer will be 1 by 4 pi epsilon naught Q naught 1 upon RB minus 1 upon RA. So this is the expression for potential difference. Now what we'll do? For finding out potential at a point, you have to just keep RB is equals to infinity, and then whether you write down RA or RB or R, they are going to be the same, and we'll get an expression for potential as 1 upon 4 pi epsilon naught. Q naught will be removed. 1 upon